like shrink those massive audio files way down, without ending up with that kind of fuzzy, low quality sound. Like, remember those old MP3 days?
Oh, yeah.
Yeah, we'd rather forget those. Well, AI is like stepping up to fix that, and it's honestly pretty amazing.
It is.
We're diving into two systems, SoundStream and AudioLM, that are kind of changing how we even think about audio.
Yeah, it's a huge change. Like, we've been stuck with these traditional codecs for so long, and they either try to, like, I don't know.
Squish it all down?
Yeah, squish the sound wave itself, which is like, it's like folding a giant map. You know what I mean?
Right, right.
Or they analyze it like a movie and just give you bullet points. That's the parametric approach.
Summarizing it.
Summarizing, exactly. Both work okay, but when you go to really low byte rates, it all just falls apart. The quality tanks.
Yeah.
And that's where SoundStream is different.
Okay, so SoundStream comes in. It's like it found this secret passage to audio compression that nobody else knew about, right? So tell me more about this residual vector quantizer. It sounds kind of intense.
It's actually pretty clever. Imagine like packing a suitcase.
Okay.
But you do it in stages.
Okay.
And each stage, you organize things more efficiently.
Right.
That's kind of what SoundStream's RVQ is doing.
Okay.
It compresses the data step by step, each time getting more refined, so you can shrink the file size dramatically, but not wreck the quality.
Okay, that's a way better analogy.
Than a multi-stage rocket.
Yeah. But does it actually work? Like, what do the researchers actually say about how it performs?
So they tested it. They put it head-to-head with, like, the big dogs, Opus, and EVS.
Oh, wow.
And the results were pretty wild. SoundStream was consistently rated higher quality by listeners, even at super low byte rates.
Really?
We're talking like a fraction the size of an MP3, but clearer.
That's mind-blowing. Faster streaming, crystal clear audio, even on a bad internet connection. This could be huge. And to top it off, they've got it running on a smartphone.
Yeah, it's true.
Wow.
The paper even have a chart, I think it's figure 1.
Okay.
It just shows it beating the competition.
This isn't just some, futuristic dream. This is
This is real.
This is happening. Okay, I'm sold. But now I need to know how it actually works. So we talked about RVQ and everything, but how does it actually take the audio, transform it, and then put it back together?
So SoundStream uses this this encoder-decoder structure. You can see it in the paper figure 2. The encoder is like the translator. It takes that complex audio waveform and turns it into something streamlined, something compressed.
Right.
And then the decoder does its magic and rebuilds it from those compressed codes.
So it's basically like SoundStream turns audio into this secret code language, compresses it down, and then decodes it back into the beautiful high-fidelity sound. It sounds almost too good to be true.
That's the power of neural networks.
Wow.
And here's what's really cool. The architecture is so efficient. You can actually change the byte rate without retraining the whole thing.
Oh, really?
Yeah. And that's almost unheard of with AI. Usually you got to reteach it for every little tweak.
Wow. Okay, so SoundStream's clearly the rock star of compression here, right? But what about actually creating audio from nothing?
Ah, yes.
That's a whole other level, and that's where AudioLM comes in, right?
That's right. A SoundStream is shrinking what exists. AudioLM is making it up from scratch.
Okay.
And it does this by treating sound like a language.
Hold on. Treating sound like a language, that's a wild concept. How does that even work?
So it's all about breaking audio down into what the researchers call semantic and acoustic tokens.
Okay.
Think of the semantic tokens like the plot of a story. They're capturing the meaning, the high-level structure of the sound.
Okay, I think I'm following. So semantic tokens are like the plot, so then what are acoustic tokens?
The actors delivering the lines.
Okay.
They're the performance, the tone, the little nuances, the specific details of how it sounds. You could have two actors tell the same story totally differently, right?
Right.
Same plot, different feel.
That's a great way to put it. So AudioLM uses these semantic and acoustic tokens to build the audio. But how does it even learn the meaning of a sound in the first place? How do you teach AI about something that's the feeling behind the notes?
That is where things get really interesting. And we'll dig into that more in the next part of our deep dive.
Mm.
So AudioLM, it actually uses another AI model called W2V BERT.
Okay.
And this W2V BERT, it's already amazing at understanding the patterns of human language,
Okay.
like grammar, how sentences fit together.
W2V BERT. Okay, I've heard whispers of this one in the AI world.
Yeah.
What's so special about it?
Imagine you give this AI a whole library full of books.
Okay.
Right? But you don't teach it what the words mean.
Oh, wow.
You don't give it the rules of grammar. It has to figure it out on its own.
Wow.
That's W2V-PyPI loop.
Okay.
They train it on a massive amount of data, text, speech, all of it.
So it's like it's deciphering this like secret code of language.
Exactly.
And then AudioLM is like tapping into that knowledge to then understand audio.
Yes.
Okay, that's amazing.
It's really cool.
But then how do you go from text and speech to like, I don't know, the sound of like a babbling brook or like a symphony?
That's the really cool part, right? It's like a lot of the same principles that we see in language, they apply to music, they apply to other audio. There's a structure there,
Okay.
a kind of like universal grammar of sound.
Okay, that's a really cool way to think about it.
Yeah.
So AudioLM uses that W2V beast BERT to understand that language of sound. And that's how it gets those semantic tokens that we were talking about.
Exactly. It's learning from a master linguist, basically,
Oh, wow.
so that it can then create things that aren't just random noise, but actually have that structure and meaning.
Okay, that makes a lot of sense. Okay, so now we've got these semantic tokens, right? Which is that high-level structure.
Right.
What about those like really fine-grained details, the actual, like the sounds themselves? That's where those acoustic tokens come
Yeah.
in.
AudioLM actually uses SoundStream's acoustic tokens as the building blocks to actually make the audio. It's like a two-step process. First, you make a blueprint, right, with the semantic tokens, laying out the story. And then it uses those acoustic tokens to like fill in the details, add the texture, the little nuances that make it sound real.
So it's almost like an architect designing a building.
Oh, I like that.
Yeah, so they have like the design and then they choose the materials and everything to actually bring that vision to life.
And that's a great analogy because that hierarchical approach is what lets audio LM make audio that's not just coherent, but also consistent over time. Think about a pianist playing a piece.
Okay.
They've got a certain style, a certain feel, and they maintain that through the whole thing.
Yeah.
Even when the tempo changes or the volume goes up and down, it's still them.
Right. They're not suddenly going to switch from like classical to jazz in the middle of like a Beethoven sonata.
And audio LM can do that with sound. Keep a speaker sounding like the same person or music in the same style, even on these longer pieces. That long-term consistency, that's really key here.
Okay, that is really impressive. But how do they even begin to train this thing? Because it seems like a monumental task to teach an AI system all of this.
It is. It's complex. But they use this really clever approach called hierarchical modeling.
Okay.
And essentially what they do is they break the training down into stages. Each stage focuses on a different part of that audio generation process.
Oh, okay. So it's like training for a marathon, right? Like you wouldn't go out and run 26 miles on day one.
Right. You build up to it.
You build up.
Exactly.
Okay.
So they start by training a model just on generating those semantic tokens,
Okay.
teaching it to understand the story.
Oh.
Right. And then they train a separate model that handles the acoustic tokens, but they condition it on that semantic information.
Hold on. Condition it. What does that mean?
It means the acoustic model isn't just spitting out random sounds, right?
Okay.
It's getting cues from the semantic tokens
Okay.
to make sure what it creates fits with that overall structure and meaning.
Okay, so the first one's like laying the groundwork.
Yes,
And the second one builds on top of it, and that's what adds those details that pull it all together.
exactly. And this approach, this hierarchical approach, has a couple of big advantages. One, it means they can train that acoustic model on huge amounts of data without needing to label it all.
Oh, wow.
Because they're not teaching it specific sounds, they're teaching it to make a sound that fits the context.
So it's like teaching someone a new language by just like throwing them into a conversation?
Yes, immersion.
Versus like, here's a dictionary, here are the grammar rules.
Exactly. They're letting the AI learn by listening, by absorbing the data itself.
That's really cool. That's a really elegant solution.
It is.
But they didn't stop there, right? The paper mentions something about splitting the acoustic modeling too into like a coarse stage and a fine stage. So why do you need both of those?
That's a great question. And it gets to another clever thing audio LM does. Remember we talked about SoundStream and its multi-stage compression?
Right, with the suitcase.
It's a suitcase,
Yeah.
packing it more efficiently each time.
Right.
Audio LM actually takes advantage of that multi-layered structure.
Oh, wow.
So the coarse acoustic model, it's focused on the big picture. The overall timbre, like if it's a voice, whose voice it sounds like.
Okay.
And then that fine acoustic model comes in and adds the really subtle things, the nuances that make it sound real.
Oh, so it's almost like sculpting, where you start with that like rough shape and then you keep refining it,
Exactly.
adding more and more detail until you've got this like lifelike masterpiece.
You got it. And that's how audio llama gets such rich, nuanced audio.
Wow, this is all incredibly impressive.
It is.
It seems like this AudioLM is capable of some, like, truly amazing things.
It really is.
But now I'm curious, like, what can it actually do?
Yeah.
What are some, like, real-world examples of this technology in action?
That is where things get exciting, and we'll dive into that in the next part of our deep dive.
Okay, so let's get to the good stuff. What can AudioLM actually do? The paper mentioned, like, generating speech, but it sounds like it's coming from the same speaker?
Right.
Even if the AI's never heard that voice before. That just sounds like magic to me.
It's really one of the coolest things, right?
Yeah.
Because remember those semantic tokens?
Yeah.
They're not just picking up the meaning of what you're saying. They're also catching things like who's talking and what their speaking style is like.
So even if AudioLM's never heard, like, a specific voice, it can still make something that sounds like them.
It can.
That's incredible. Okay, but what about, like, controlling what it actually says? Can you tell AudioLM say this, or is it more like it just kind of does its own thing?
No, you can definitely steer it.
Okay.
And that's another place those semantic tokens are really important. They did these tests where they basically gave AudioLM like a phonetic spelling test.
Oh, that's cool.
Right. Okay, now generate the sounds for these words and phrases.
Okay, and how'd it do?
Nailed it. Even with tricky words, complex phrases, it was making the sounds that matched what they asked for.
Wow, so it really gets that connection
It does.
between those kind of abstract tokens and what we actually hear.
Yeah.
That's wild. Okay, but what about those acoustic tokens? How do we know those are actually capturing, like, important stuff about the sound? Not just, how it kind of sounds on the surface, but, like, who's talking or where it was recorded.
Great question. So to test that, they took things a step further.
Okay.
They trained a whole separate AI just for speaker classification.
Okay.
Like imagine it can listen to a voice and tell you who it is.
Like an audio fingerprint expert.
Exactly.
That's so cool.
So then they took AudioLM's output, right? The stuff it made,
Okay.
and fed that to the speaker classifier, sometimes with different semantic tokens just to mix things up.
Oh, clever. And what happened? Could it still tell who the speaker was, even in the made-up audio?
It could.
Yeah.
Even when the words being said were totally different, the acoustic tokens were still giving away who was speaking.
So it's like those acoustic tokens are more than just, like, surface level, right? They're really grabbing something deeper.
Yeah, exactly. Like AudioLM is learning this sort of universal representation of sound.
Oh.
It's not just memorizing specific examples from the data, it's figuring out the underlying rules of how sound works.
Wow. Okay. So if it can do that for any sound, imagine the possibilities. Making audio in any language, crazy realistic sound effects for games and movies, even composing totally new kinds of music.
Right.
That's mind-blowing. But before we go completely down that rabbit hole, what are some of the things that the researchers specifically said they're excited about using this for?
So they were really hyped about speech synthesis and music generation. Imagine like personalized text-to-speech, but it sounds completely natural. Like
Oh.
actually expressive, like a real person.
Hmm.
Or, AI tools that can help musicians write, arrange, even perform their music in ways they've never even thought of before.
So it's like suddenly all these creative fields, like music and voice acting, are way more open to people.
Okay.
Anyone with a story or a song in their head, now they've got these tools to actually make it real.
And it goes deeper than that even, right? Because
Yeah.
by looking at how AudioLM learns and creates, we get to understand our own minds better.
Oh.
It's like using AI to hold up a mirror to how we communicate, how we make art.
It's like we're at the very beginning of, like, this whole new world of audio.
It really is.
And the possibilities are just
endless.
endless. But like with any technology this powerful, we have to think about the downsides, right?
Yes.
If you can make, like, perfectly real sounding audio,
Yeah.
it means misinformation, deep fakes, all that gets way harder to spot.
It's true. Those are big questions.
Yeah.
And as this tech gets even better, we've got to be really careful, make sure it's being used for good.
It's a powerful tool, but we need to use it responsibly.
We do.
Well, we have covered a lot of ground in this deep dive, from those, like, nitty-gritty details of how SoundStream and AudioLM work to, like, the mind-blowing things they can do and all the big ethical questions we have to be asking.
It's been quite the journey.
It has. So for listeners, if any of this has, like, sparked your curiosity, definitely check out those research papers. We'll link them in the show notes. But until then, keep exploring, and we'll catch you on the next deep dive.